Hello, Mr. Simpson here, back with Chapter 10, Section 2, Properties of Liquids. Please take a moment to pause the video to copy down the learning objectives. Lots of notes and discussion here in this section. At the end of Section 1, I talked briefly about how intermolecular forces affect phase changes that we're familiar with, properties that we're familiar with, like boiling point. So the idea that intermolecular forces must be broken in order for a liquid to become a gas. And so understanding the strength of the intermolecular forces would help me to predict ranging orders of a property like boiling point. In this section, we're going to talk about some additional properties of liquids. Again, their strength and weakness and how they're affected will tie into the intermolecular forces we learned about in the first section. Okay, the first property is viscosity. You can see the definition here, a measure of a resistance to flow. So you may have heard this term with regards to your automobile's oil. High viscosity oil has a greater resistance to flow, and you can see here in a second as it affects temperature and such, that would be important. Okay, so things like water, gasoline, and that flow freely have low viscosity, where motor oil, syrup, honey have a high viscosity because they do not flow very freely. Now here's how it's related to IMFs. IMFs between the molecules of a liquid, the size and shape and the temperature determine how easily this flows. Okay, so the more complex the molecule and the stronger the IMFs, the more difficult it is for those molecules to move past one another, so the greater this viscosity. So with regards to our conversation here in this chapter about intermolecular forces, the stronger the intermolecular force, the greater the viscosity. As temperature increases, that's going to make the molecules move faster. They're going to move past one another faster, so viscosity would decrease as temperature increases. Okay, so that's the same type of conversations we want to have with these properties in this chapter, similar to what we saw in Section 1. In addition to properties like viscosity and surface tension and capillary rise in this section, I also want to talk about cohesive and adhesive forces. Okay, so here first we're going to talk about cohesive forces, and you can see a little diagram here that helps to explain what we're talking about. First, cohesive forces are those forces between identical molecules of a substance. So the same molecule within the substance. So these intermolecular forces that we've been talking about. And you can see an example of a cohesive force in water droplets. So what happens is all these forces are being applied to all surrounding molecules, except those on the surface. The surface molecules are exposed because they don't have the same kind of surrounding. So in an attempt to limit that exposure, you get these molecules start to pull each other, and you get that kind of rounding, bubbling effect because that shape provides less surface area, less surface molecules, and so that's an effect of the cohesive force of those molecules being attracted to one another. You will find this diagram in the textbook and the PowerPoint, but I will pause the video. I would suggest pausing the video for a second to get down some of these characteristics of cohesive forces. Next are adhesive forces, and so the difference here is that these are forces of attraction between two different molecules. Okay, so not the same molecule, all the same molecules in a substance, but for example, the force of attraction between the water and the surface. So that's an example of adhesive forces. Go ahead and pause the video here to get down some of these notes on characteristics of adhesive forces. I think this diagram here of the meniscus of water versus mercury in a glass tube is a good explanation and distinction between cohesive forces and adhesive forces. In this tube on the right, water, you can see the meniscus is concave down because the forces of attraction between the water molecules and the glass tube are greater, or the adhesive forces are greater than the cohesive forces, than those forces of attraction between all the different water molecules near the surface. You see just the opposite effect in mercury. Mercury is concave up here, because the forces of attraction, the adhesive forces between the mercury molecules and the glass are smaller than the cohesive forces of attraction between all the different mercury molecules. So I think that example kind of shows best the difference between cohesive and adhesive forces and what will happen when one is stronger than the other. Two more properties to talk about in this section. The next one is surface tension. You see the definition here, the energy required to increase the surface area of a liquid. Okay, so increase the surface area, make the surface area spread out. You can see some notes here about surface tension, so go ahead and pause your video to get those now. This diagram from your textbook shows the strong surface tension of water and how an insect can sit right on top of the water there without breaking the molecules apart. This is an example, again, of the cohesive forces of water. The other property to cover is capillary action. So you can see this example here. If a porous material comes in contact with a liquid, the liquid will move through the surface of that porous material. Okay, this is again some more definitions of what's happening here, but this is an example of the adhesive forces being strong. So those forces of attraction between the molecules here attracting and the porous material are what's pulling that liquid upward against gravity. All right, that's it for the second section of Chapter 10. We're going to apply a lot of these properties of liquids to our intermolecular forces from Section 1 to distinguish, when these properties would be changing or higher or lower.